Hi, I'm David Vegh, and I'm at the CTP at Queen Mary University here in London. And today I'm going to give you a lecture on holographic Fermi surfaces. I will first give a short review of Fermi surfaces, just in case you've never heard of them. And then in the second longer part of the talk, or this lecture, I will discuss how to find Fermi surfaces via the ADS-CFT correspondence. So now the topic of holographic Fermi surfaces is at the interface between condensed matter physics, gravitational physics, and quantum field theory. And this was made possible by the invention of the holographic duality, which I will also introduce. I will talk about different asymptotically ADS geometries, and I will also explain how to compute correlation functions in the field theory using the gravity dual. Condensed matter physics deals with the physical properties of matter, and matter comes in different forms and phases. For instance, you can have solids, liquid phases, or superconductors. There are a plethora of different phases of matter, and these are all called condensed phases of matter. Now, in quantum field theory, you can get a non-zero density if you turn on a chemical potential for a given conserved charge, such as the electric charge. Then charged particles will accumulate in the system. Now, there are two kinds of particles, bosons and fermions. You can have either in the system or both. And bosons are happy to occupy the lowest energy single particle state. And then they just form a condensate with probably some interesting properties. The fermions, on the other hand, have to satisfy the Pauli exclusion principle. So after the lowest states are filled, you can only add fermions if you put them into higher and higher energy states. So you can keep lowering the energy of the system by adding fermions until you reach the chemical potential. Okay, so in a Fourier space, momentum space, this is what it looks like. So I drew a two-dimensional picture, and kx and ky are the two wave vector axes here. The boundary between the occupied and the unoccupied regions is the Fermi surface, which is just a circle in this case, because I assumed a rotationally invariant two-dimensional system. Okay, now the energy difference between the highest energy single particle states, so up here, near the surface, and the lowest energy states here in the middle, in such a quantum system where you consider non-interacting fermions, and we are also at zero temperature. So this difference of energies is the Fermi energy. So this is usually of the order of a few electron volts. So here is the first corresponding exercise for you. What is 1 electron volt expressed in kelvins? So this the scale of an electron volt is considered a UV scale in condensed matter physics. So the Fermi surface for a real material is not as simple as this, because there is typically a lattice of ions, and the electrons swim on top of this charged background. So this means that the single particle states are different from those in vacuum. The system in real space forms a lattice, and you can talk about the fundamental or primitive cell in this lattice in real space. A particular, very special primitive cell is the so-called Wigner-Seitz cell. Okay, so since you have a lattice in real space, you also have a periodic momentum space, which is also called a reciprocal space, and you get a reciprocal lattice. So in neutron or X-ray diffraction experiments, you can determine the reciprocal vectors of the lattice by staring at the diffraction pattern. And then after that, you can figure out the structure of the crystal where the atoms or the ions lie in the lattice. Okay, so the primitive cell of the reciprocal lattice is called the Brillouin zone. And it can come in many shapes and forms, and I drew here a two-dimensional example where it has this hexagonal shape. So inside it, you can see the Fermi surface. So it's here, this black line, which is now not a circular object because the crystal lattice has broken the rotational symmetry in the system. So just like in this case, it doesn't even have to be simply connected. Okay, so these are complications. These are very important complications in real materials, but we are not going to further discuss them in this lecture. So let's go back to the circle. Energy is measured from the chemical potential. And the low energy excitation can be, for instance, when you move an electron from this state to this one here outside the Fermi surface. So if you did this in the Dirac sea, then these two dots would represent an electron out here and a positron here. But in this case, this is an electron, and this is a hole in the system. Okay, so these are the low energy excitations, and there are plenty of them. So these materials with such a Fermi surface form a metallic state. We are going to consider circular or spherical Fermi surfaces. So then you can talk about the radius of the Fermi surface, which I'm going to denote by Kf. And this F stands for Fermi. So now electrons obey the Fermi-Dirac statistics as opposed to Bose-Einstein statistics. And identical fermions in equilibrium, the average number of fermions in a single particle state that I denoted by I. So this Ni is given by the so-called Fermi-Dirac distribution, which I also plotted here. Okay, so this is the formula. Kb is Boltzmann's constant. T is the temperature of the system. I labels the single particle state, and epsilon I is the energy of the single particle state. And finally, mu here is the chemical potential. At zero temperature, this function gives you this step function here with a very sharp step here. And as you turn on a non-zero temperature, it is this dashed line, this smoother function. So up to this point, we've been talking about non-interacting electrons and single particle states. We can now imagine adiabatically turning on the interaction between the particles in the crystal. And then the non-interacting Fermi gas will turn into a so-called Fermi liquid, which is then described by Landau's Fermi liquid theory. If you now introduce an extra particle into the system, then it will be dressed by interactions, which is represented here with this blue cloud around the particle. And we're going to call these dressed particles quasi-particles. As the interaction is turned on, the spin, the charge, and the momentum of the fermions corresponding to the occupied states, these remain unchanged, but their dynamical properties, for instance, the mass, gets renormalized. And there can be orders of magnitude differences here, so they do receive a huge contributions from the interaction. The Fermi surface can also change when you adiabatically turn on the interactions. But the bottom line is that you can still describe the system basically as you do in the case of non-interacting fermions in a Fermi gas, but where you replaced these non-interacting fermions with interacting quasi-particles. The interactions do not need to be small. So in principle, you would not expect a one-to-one correspondence between the states in a non-interacting system and those in a Fermi liquid. But quite surprisingly, many metals are described by the Fermi liquid theory. For instance, the resistivity, which is the inverse DC conductivity, typically in these materials scales quadratically with the temperature. Okay, so if you want to derive this, then you will need some background lattice which can slow the particles down. Otherwise, you'd get an infinite DC conductivity. Okay, so the underlying reason for the ubiquity of Fermi liquids is that not all of the phase space is available. For instance, you cannot scatter particles into single particle states which are already occupied inside the Fermi surface. You can also understand this from an RG perspective. The Fermi liquid theory is an RG fixed point with basically no relevant operators. So in this RG flow that I'm talking about, you move closer and closer to the Fermi surface. So in this case, to this circle, and not to the origin momentum space, which is usual in particle physics. You can read more about the RG flow of Fermi liquids in Polchinski's paper that I gave in the list of references. Okay, so one famous exception to the statement that there are no relevant operators in this theory is it's a marginally relevant operator which couples two particles on antipodal sides, antipodal points of the Fermi surface. So for instance, here and here. This then gives an attractive force which at low enough temperatures makes these two quasi-particles form a bound state, the so-called Cooper pair. The Cooper pairs are bosons which can then condense. And this is in fact the mechanism in a BCS superconductor, or a low temperature, low TC superconductor. So since this operator is marginally relevant, the superconducting phase can only be achieved at very low temperatures, so you can think of a few kelvins for the phase transition. An important object that we will be focusing on in this lecture is the single particle retarded Green's function, so this GR, and it's defined by this formula here. Theta of t is the Heaviside function, so it's 0 for t less than 0. And these curly brackets indicate the anti-commutator of these fermionic operators here, psi and psi dagger. You want to evaluate this correlation function in a thermal field theory at a non-zero chemical potential mu and temperature T. The result is something like this. So now we are in Fourier space, omega and k wave vector. So here k perp is the distance from the Fermi surface. So basically in our case it's going to be just k minus kf. And k perpendicular is multiplied by Vf, that is called the Fermi velocity. It's just basically a constant at low enough frequencies. Omega is the energy measured from the Fermi energy. And here this sigma is the self-energy. And for a Fermi liquid, and this is quadratic in omega. And there's a factor of I here. So you see this is for low, very small omegas, this omega squared is much smaller than the energy of the particle. So this means that this particle is a long-lived quasi-particle. Finally, this z in the numerator is the residue of the pole on the complex frequency plane. And this stays finite as you move closer and closer to the Fermi surface, whereas k perp goes to 0. There are plenty of Fermi liquids in nature, but there are also non-Fermi liquids. In these materials, the Fermi liquid theory breaks down. A simple example is a system of interacting fermions in 1+1 dimensions. And this is called a Lottinger liquid. So in 2D, you can bosonize fermions, so you can imagine that the elementary excitations can behave very differently from what you'd expect from a Fermi liquid. Other examples can be found at so-called quantum critical points. These are points in the phase diagram of a material where a phase transition takes place at exactly 0 temperature, as some other parameter is changed. So you keep the temperature at equals 0, you change some other parameter. If you're a theorist, just some parameter in the Lagrangian. If you're an experimentalist, it can be pressure, background magnetic field, or something else. And then you get a second order phase transition where you find something interesting. A prime example for this is what you can see in the normal phase of optimally doped high TC superconductors such as cuprates or pnictides. So TC here is the phase transition temperature, and above this temperature the material is in a non-superconducting phase. It's a metal, which is it turns out to be a non-Fermi liquid. This is also called a strange metal. For non-Fermi liquids, Fermi surface can still be present, but there may not be long-lived quasi-particles anymore. So you can imagine here's the Green's function in Fourier space. You can imagine that the self-energy, which was quadratic in omega for a Fermi liquid, now you can replace this exponent 2 here with a number that is smaller than 1. Then this will dominate over the energy, and you don't have a long-lived quasi-particle anymore. And furthermore, the residue might also vanish as you go with K-perp to 0 as you approach the Fermi surface. Non-Fermi liquids have anomalous thermodynamic and transport properties that you can measure. For instance, the resistivity of high TC superconductors in the normal phase goes linearly with the temperature. So, whereas for Fermi liquids, this was a quadratic behavior in the temperature. So very different. Understanding non-Fermi liquids is a very important problem in condensed matter physics. You can start building models where you couple the Fermi surface, for instance, to a bosonic field or do something else. But the resulting theories are often ill-defined. Feynman diagrams diverge even in some large n limits. So we're not going to do that. Instead, in the remainder of this lecture, we want to ask the question whether we can find non-Fermi liquids in the controlled laboratory of the ADS-CFT correspondence. The anti-de Sitter conformal field theory correspondence was proposed by Maldacena in 1997. Sometimes it's called the gauge-gravity duality, which is perhaps a bit more general thing. It is the most successful realization of the so-called holographic principle. This is a property of quantum gravity that states that the volume of space can be described by a theory on the boundary of that volume. The holographic principle came from black hole thermodynamics. It was observed that the maximal entropy in a region scales with the radius squared and not radius cubed, as you might expect. So in ADS-CFT, the gravitational theory is a string theory on a d+1 dimensional asymptotically anti-de Sitter spacetime. And the dual theory lives on the boundary, indeed, in d-dimensional spacetime. So it says 1 less dimensions. Here is the artist's impression of empty ADS space. Space does have a boundary, which is indicated by this rectangle here. And that's where the conformal field theory lives. So this is a d-dimensional boundary. But ADS has this extra radial direction. And we're going to call this space the bulk. So gravity is here, and there's no gravity on the boundary theory. So according to the correspondence, this ADS space is the dual to the vacuum state in the field theory. We can turn on a non-zero temperature by placing a black brane or black hole inside ADS. The resulting geometry will still be asymptotically ADS, so near the boundary, it will look like ADS. Black holes come with a Hawking temperature, and this will be the temperature of the dual field theory as well. And finally, we need one more ingredient. We like to mimic condensed matter systems, so we also need to turn on a chemical potential. And according to the correspondence, the dual of a conserved current is a gauge field in the bulk. So we'll consider charged black branes in ADS space. Before considering more relevant geometries, let's first talk about empty ADS spacetime. So D plus one-dimensional ADS can be defined as the hyperboloid given by this equation here. You can think of the left-hand side as the length of this vector x, which is an element in the R2, D flat ambient space. So this ambient space has two time-like directions. It's a bit weird, but ADS has only one time-like direction. So that's perfectly fine. And this equation says that the length of this vector x is just a constant given by L, which is just the ADS radius. Then the metric on ADS space is just the induced metric on this hyperboloid. So if you define ADS this way, then you run into a problem. Namely, the hyperboloid has closed time-like curves. For instance, ADS2 is depicted here. The closed time-like curves are these circles on the surface that wrap the hyperboloid. And they correspond to rotations in the x-1, x0 plane. So what you need to do is you need to consider the universal cover of the hyperboloid, where you sort of unwrap this closed time circle, so that now it's just an infinite line. This equation can be solved by defining coordinates on the hyperboloid, and here I give coordinates on the so-called Poincare patch. Okay, so the chart with these coordinates covers half of the hyperboloid, so it doesn't cover all of space-time. And here you have various coordinates like t for time, z here is the radial direction in ADS, and x, this is a vector, which is a d-1 dimensional vector. And if you plug these formulas back into the equation here, you can see that they satisfy, you get L squared on the left-hand side. Okay, so here's an exercise for you. Show that the induced metric in the Poincare coordinates defined this way, the induced metric is given by this formula here. So you see that this is a conformally flat metric, which means that if you multiply it by a certain function, in this case z squared, then you get back the flat metric, just dz squared minus dt squared plus dx squared. So one very useful consequence of this is that in this Poincare patch coordinates, null rays move the same way as if it were just flat Minkowski spacetime, because on a null word line, ds squared is of course 0, so it doesn't matter whether you divide by z squared or not. You can think of this space in these coordinates as if it had a constant gravitational field, so massive objects fall down in the positive z direction. Here is another exercise for you. Show that the metric, the Poincare patch metric, satisfies Einstein's equations with a negative cosmological constant, lambda. And then you'll be able to relate lambda to L, the radius of ADS space. You can definitely do this by hand, but I do recommend using Mathematica. Mathematica doesn't know about tensors, but you can use a Mathematica package, for instance, Matt Hedrick's differential geometry code that you can download from his website. And then this calculation will be quite simple. As I mentioned, this space, ADS space, has a conformal boundary, which is at z equals 0 here, where the metric blows up. The boundary is at an infinite distance away from bulk points that you can check. Nevertheless, null rays can reach the boundary, even if massive objects cannot. So we'll need to put some boundary conditions on the boundary, on this boundary. I told you that the Poincare patch only covers a part of ADS space. So let's try to visualize this. For instance, let's consider the case of ADS3. We can define the so-called global ADS coordinates via these equations. So these are tau, rho, and phi, and they are related to the ambient space coordinates via these equations here. ADS3, you can think of it as an infinitely long cylinder, and this vertical direction is this tau direction. This is the global time, and you see sine of tau and cosine of tau appear in the equations, so we assume that we unwrapped this compact angular time-like direction. Rho is a radial direction running from 0 to infinity, but in this figure I compactified it, so rho equal infinity is the surface of the cylinder. And finally, phi is an angular direction inside the cylinder. So in these coordinates, the global ADS coordinates, the Poincare patch will be this wedge depicted here, this blue wedge. The boundary of the Poincare patch will be this diamond, this bit here and this here and what's behind the picture. These, the top and the bottom of the wedge, these are called the Poincare horizons. Okay, so this picture was drawn using Mathematica by Louis Sword, my student. I obviously then drew these lines here by hand. So another useful exercise for you is to try to generate this figure in Mathematica. Let us now turn on a non-zero temperature in the field theory. As I mentioned before, the bulk dual will contain a black hole with the same Hawking temperature. We would like to preserve translational symmetry, so the event horizon of the black hole will be just a plane. So what we have is a black brane inside ADS spacetime. The metric is given by this expression here. The only difference compared to the Poincare patch of ADS is that we have included this f of r function here and here, which is called the emblackening factor. And this is only a function of the radial direction here, which is r. I have also switched to a reciprocal radial coordinate, so this r here corresponds to 1 over z on the previous slide. In this coordinate system, r goes to infinity is the location of the ADS boundary. And you see that as r goes to infinity, this f just approaches 1, and the geometry is locally then just ADS of radius L. On the other hand, if you decrease r, then eventually this function vanishes at exactly at r equal r naught. And since this space-time is static, this is the location of the event horizon of the black brane. Okay, so here's another exercise for you. Show that this metric here satisfies Einstein's equations with a negative cosmological constant. And again, I do recommend using Mathematica. Now, the horizon where this f of r function vanishes has a Hawking temperature, and I claim that this is given by this formula here. D is just the dimension in ADS d plus 1. R naught is the constant appearing the emblackening factor over 4 pi L squared. L was the radius of the ADS space in the UV, meaning R goes to infinity. Your exercise now is to compute this temperature. You can use this trick. It's a very useful trick. You analytically continue the metric into Euclidean signature. So in Euclidean signature, space caps off at r equal r0. So I depicted imaginary time here, this tau direction here, as a circle because it's compactified. And this r is this radial direction. So this two-dimensional surface smoothly caps off at r equal r0. So there is nothing behind the horizon here. There is no horizon. Okay, so the period in imaginary time is beta, which is 1 over the temperature. And you want the space to smoothly end at r equal r0. So you have to carefully set the period in order to avoid a canonical singularity here. So the exercise is to show that when the space smoothly caps off, the temperature is given by this formula here. When you have a compact imaginary time direction, the boundary of the bulk space has also a compact time direction with the same periodicity. So this way you can see that the dual CFT is at the same temperature as this Hawking temperature here. Using ADS CFT, we now would like to compute field theory correlation functions using the ADS dual, the bulk dual. There's a dictionary relating the two theories. According to this dictionary, local operators correspond to certain fields in the gravity dual. If you want to compute, say, the retarded Green's function of an operator on the boundary theory, then you can study the corresponding field in asymptotically ADS spacetime. So this way you can study the behavior of the field theory at strong coupling. Now the CFT has conformal symmetry, which is part of it is the scaling symmetry. So under dilatations, where x goes to lambda x, operators get multiplied by a factor lambda to the minus delta, where this delta is the scaling dimension of the operator O. The mass of the bulk dual field is related to the scaling dimension delta. For instance, for a scalar field, which has a mass m, this is the relationship. So here again, d is the dimension of the CFT, and L is the ADS radius. For computing two-point functions of an operator, it will be enough to consider the quadratic action for the corresponding bulk field. So let's first consider a scalar field that we denote by phi. We're going to assume that this field does not backreact on the geometry. So we are in a probe approximation limit. So this means that we have a fixed background geometry, G mean nu, which I am not specifying yet. And on top of this background, there is a scalar field propagating. At this point, we only assume that the geometry is some kind of asymptotically ADS geometry of d+1 dimensions. So therefore, the dual field theory is d-dimensional. And note also that we will be doing the calculation directly in Lorentzian signature, which is an advantage of this formalism. We're going to assume translational symmetry in the boundary theory and in the bulk as well. And therefore, we can immediately go to Fourier space where modes of different frequency and wave vector decouple. So we write phi as this Fourier transform here. And we're going to separate this one form into the frequency part and the wave vector part. We now would like to compute the equation of motion for the scalar field. This is just the well-known Klein-Gordon equation in curved spacetime. We assume that the background metric is diagonal, so this GMN is 0 if m is not equal to n. Then the equation of motion for the scalar field will be given by this expression here. G is just the determinant of the metric, and this K is just a number which is the length of the wave vector. And again, omega here is the frequency of the field, and m is just the mass of the scalar field. The goal will be to solve this equation with certain boundary conditions, and from the solution we will be able to determine the two-point function of the dual operator in the field theory. Okay, so we assumed an asymptotically ADS background geometry. This means that as we approach the boundary of the spacetime, it will look like pure ADS space. In R coordinates, this will happen at large R, and the boundary is at R equal to infinity. If we want to figure out the behavior of the scalar field in this so-called UV region, we can simply plug in the metric components for pure ADS, which are given here. So these are the components, and if we plug these into this equation, then we get the following equation here. So the boundary of ADS is at R equals to infinity, and we'd like to solve this equation as R goes to infinity. And it turns out that the solution will be a power law. If we plug in the power law ansatz, phi of R is equal to some constant C times R to the lambda, and then expand the equation of motion at large R, then the leading terms in the equation of motion will be these terms here. And by the equation of motion, this should vanish. So this equation will determine the possible values for lambda. Now the equation of motion is a second-order differential equation, so we will get two independent solutions, and therefore two possible lambdas from this second-order equation. So possible values for lambda are delta minus d, or minus delta, where delta was the scaling dimension of the dual operator. And I gave you the formula again that relates delta and the mass of the bulk field. Okay, so if you plug in these two lambdas, then you get the general solution for phi, which is some undetermined coefficient A that can depend on the frequency and the wave vector times that power law, and then there is another coefficient B times R to the minus delta. So near the boundary of our spacetime, the solution will behave like the sum of these two power laws. For both of these independent solutions, this one and this one, there are also subleading terms, which I didn't write here. So these are suppressed by integer powers of R. If you determine these two functions, A of k and B of k, then according to the ADS-CFT dictionary, you can compute the two-point function of the operator dual to the field phi. And this will be some positive constant, which won't be important for us, B over A. And that will be the two-point function in the boundary theory. So at this point, we just sum these two independent solutions, and I could have written here another constant and another constant here, two different constants, so this ratio is not determined at this point. We need to set a further boundary condition in the IR at the horizon. That now will fix this ratio, and we can actually compute the two-point function. In the UV, we have a geometry that asymptotes to ADS. And in the IR, we assume that there is a horizon somewhere in the geometry. For computing a retarded correlation function, one needs to specify an ingoing boundary condition at the horizon. Okay, so what does this mean? Let's now go back to the equation of motion and investigate what happens near the horizon. Okay, so here's the equation of motion. For our black-brane geometry, there was an emblackening factor f of r, which vanished at the horizon at r equal r naught. So we can just Taylor expand it there, and you get this linear function, and f naught is just some constant. The metric components are then these equations. If you plug these into the equation of motion here, then you get this other equation. So we would now like to study how the scalar field behaves in the vicinity of the horizon. And so we write this ansatz. We are again searching for some power law, but now in terms of r minus r naught. If you plug this ansatz into this equation, then you get this algebraic equation that determines lambda. And again, you'll have two solutions for lambda because it's a second order equation. Now the planar black hole came with a Hawking temperature, T. You can calculate that it is related to this f naught here via this formula. Now you can express f naught using this formula in this equation, and then you can solve it for lambda. Then you get two solutions for the exponent, which are written here. So this is plus or minus I omega over 4 pi t. Okay, so what does it mean? Now, if we go back from Fourier space to real space, then the r and t dependence of the scalar field will look like this. So this is from the Fourier transform, and this is the behavior that we just computed. So now you can see that this solution, these are waves going into the black hole or coming out of the black hole. You can set this exponent to say 0 to see which way the wave fronts move, and you'll see that for an ingoing solution, you'll need to pick the negative sign here. Okay, so here's the bulk picture. This is the radial direction, the horizontal direction. And this is the UV at r equals infinity. That's the ADS region. And this is the event horizon. So this arrow indicates that we picked the ingoing solution. Then now you have to solve this equation, the wave equation, to figure out what the A and B coefficients are. And the ratio will give you the two-point function in the boundary theory. Let's now summarize the calculation of the boundary retarded Green's function. So to the operator, there is a corresponding bulk field, and we need to study the bulk wave equation for that field. For a retarded correlation function in the boundary theory, we will consider an ingoing boundary condition at the horizon for the bulk field, represented by this arrow pointing towards the horizon. And the behavior of the bulk scalar field will be like this. After setting this boundary condition for the scalar field, we want to solve the equation of motion in the bulk to see how this ingoing solution evolves into the sum of the two independent solutions in the UV. And therefore we can compute the prefactors A and B. And the solution in the UV will behave like this. And finally, from this expansion, we just read off the Green's function by taking the ratio B over A. So you can think of B as the expectation value, a response to a source, which is the A number here. So you turn on a source, you get some expectation value, a linear response. You can also think of it as a quantum mechanical scattering experiment. There's a wave here, there is some potential here in the middle, and there are two different waves on the other side. For generic asymptotically ADS geometries, even the seemingly simple wave equation is hard to solve. You can try to solve it numerically or by taking some limit, for instance, a small frequency limit, or considering a limiting case of the background geometry itself, such as a low temperature black hole. So T goes to 0 limit can also be investigated. Another option is going to lower dimensions, where you have a chance to proceed with analytical calculations. For instance, gravity in 3 dimensions is very special because massless graviton has 0 degrees of freedom locally, so there are no gravitational waves. So you can solve Einstein's equations with a negative cosmological constant, and you get this rotating BTZ black hole geometry. So if the cosmological constant were 0, and we are in vacuum, then the Ricci and the Weyl tensors are 0, and therefore the Riemann tensor is also 0, and you just get flat space. So it is interesting that with a negative cosmological constant you can get something non-trivial, like this black hole here. So the metric is given by this formula. R is some radial direction, t is time, and theta is an angular coordinate. And it is asymptotically locally ADS3. R plus and R minus are two constants. These are the inner and outer horizons for this rotating black hole. Now this geometry is not only asymptotically locally ADS, but it is also locally ADS3 everywhere. So you can think of it as an orbifold of ADS3. ADS3 is the covering space of this geometry. And the exercise for you will be to solve the scalar equation of motion in this space-time. And for that, we'd like to go to new coordinates. So we replace t, r, and theta by capital T, not to be confused with the temperature, capital X, and rho. These new coordinates, which I want to define implicitly via these equations here. Okay, so you can check that the metric in these new coordinates will be this simple metric here, minus sinh squared rho, dt squared plus cos squared rho, dx squared plus d rho squared. So the metric in these new coordinates does not depend on the capital T time or the capital X spatial directions. So we can go to Fourier space and take this plane wave ansatz for the scalar field. And this phi of rho, this will be only a function of the radial direction. So here I introduced, instead of omega, I wrote kt, and instead of the k wave vector, I wrote kx. These are the frequency and the momentum with respect to these t and x time and space variables. Okay, so part of the exercise for you is that you should be able to derive the wave equation, which is given here. So phi double prime of rho plus 2 cotangent hyperbolic 2 rho, phi prime plus this expression here multiplying phi of r, and that is equal to 0. And m is just the mass of the scalar field inside the BTZ space-time. Okay, so the exercise for you is to solve this wave equation. This you can do analytically. You get two independent solutions, and you want to combine them so that the solution at the horizon is an ingoing wave, like we discussed before. Then you take this solution, and then you expand it in the UV. And from the expansion, you take the ratios of the coefficients of the two power law functions, and that will give you the retarded correlation function. So if you cannot solve this equation with this rho independent variable, then you can change the coordinate to coordinate z, which is equal to tanh squared of rho, and this might help you simplify the equation. Okay, so what you get, I'm giving you the result here. So the retarded correlation function in terms of kt and kx will be proportional to the ratio of these gamma functions, where is delta plus is the conformal dimension, the scaling dimension of the dual operator, 1 plus square root of 1 plus m squared, and I defined a delta minus as well with the minus sign here. So these two constants appear in the gamma functions, and kt and kx also appear. Okay, so you should get this result from this calculation. That is the exercise. And once you have this result, you can analyze the behavior of this retarded correlation function. You can plot this function on the complex kt plane. That's the complex frequency plane at a fixed value of kx. Okay, so since this is the retarded correlation function, all the poles of the function have to be on the lower half plane. Otherwise, if you have a pole on the upper half plane, that would signal an instability in the system. So part of the exercise is checking that all the poles are on the lower half plane as required. And finally, you can go back to the 2002 paper of Sun and Starinets and compare this formula with their result. Now you can compute correlation functions at finite temperature, meaning a non-zero temperature in ADS-CFT. But in order to find Fermi surfaces, we'll need a couple more ingredients. So first of all, we need to add a chemical potential to the system. Okay, so let's consider a d-dimensional CFT with some global U1 symmetry that has a gravitational dual. At a finite charge density, the system can be described by a charged black hole in d+1 dimensional anti-de Sitter spacetime. And according to the ADS-CFT dictionary, the current corresponding to the U1 symmetry, G mu in the CFT, is mapped to a U1 gauge field in ADS. Okay, so we're going to denote that gauge field by AN, and F is the field strength, and the action for such a gauge field coupled to gravity can be written as this action here. So R is just the Ricci scalar, here's a negative cosmological constant, and this is the Maxwell term, and GF is some gauge coupling. And finally, L is the curvature radius of ADS as before. So that's our assumed gravity action. You can compute the equations of motion, and they are solved by this planar ADS Reissner-Nordstrom geometry, which describes a planar charged black hole. So the form of the metric is the same as before. There is this f of r in blackening factor, which is now a bit more complicated compared to the uncharged case. There is this extra term that scales differently with r, the radial direction. M is related to the mass, and Q to the charge and to the chemical potential of the boundary dual. And the gauge field is also turned on, and we go to a gauge where only A, the time component of A, is non-zero, and is given by this formula here. R0 is the location of the horizon where f of r vanishes. And so from that you can compute m if you plug in this formula here. M is equal to these powers of R naught. Note that the gauge field also vanishes at the horizon at R equal R naught. So then you get 1 minus 1 here. And this is a condition that comes from the fact that the gauge field should be regular in ingoing Eddington-Finkelstein coordinates. Okay, so I'm just giving you a formula here for the chemical potential in the boundary dual. It is related to this Q constant via this formula here. And I just define this CD constant, which is only a function of the dimensionality here. And as before, using the trick of analytic continuation to Euclidean signature, you can compute the temperature of this black hole, and it turns out to be this expression. If you set Q equal to 0, then you recover the previous result for our for the planar black hole. Okay, so this is the ADS Reissner-Nordstrom geometry, and this will be our playground where we can find interesting Fermi surfaces. So when this T is of order 1, then the geometry is a bit complicated. But here's an exercise. Show that at T equals 0, the near horizon geometry simplifies drastically, and it is just ADS2 cross RD minus 1. So ADS2 is the time and the radial coordinates, and the spatial directions sort of decouple from the ADS direction. Okay, so if you realize this, then you will be able to describe the behavior of the system at 0 temperature and even at parametrically small temperatures as well. Now we have the background geometry, and in order to find Fermi surfaces, we also need to add a fermionic probe in the bulk. This will be the dual field to a fermionic operator in the boundary theory, and we are interested in computing the retarded correlation function of this fermionic operator. Okay, so Dirac field in the bulk can be described by this action here. Here's the kinetic term and the mass of the field psi. Okay, so what do these mean? Well, psi bar is just psi dagger multiplied by this gamma matrix here. And there is a difference between the underlined indices and the indices which are not underlined. These are curved space indices versus tangent space, flat space indices. This D differential operator, it contains the partial derivative. It also contains this omega ABM, which is the spin connection, and the commutator of the gamma matrices. And finally, the field couples to the background gauge field at AM. Remember, in our geometry, AT, only the time component was non-zero, and the coupling constant here is just the charge of the fermionic field. Okay, so now you want to solve the Dirac equation that comes from this action in the ADS Reissner-Nordstrom geometry. Compared to the scalar field, there are complications, mainly because this psi field contains many degrees of freedom. It has many components, and the Green's function of the dual fermionic operator is also a matrix. But otherwise, the calculation is essentially the same as before, same as for a scalar field. We want to set an ingoing boundary condition at the charged horizon of the planar black hole. You evolve the equation to the UV and read off the retarded Green's function at the ADS boundary. Okay, so you can also mimic this calculation by doing the same thing, but not for a fermionic field, but only for a charged scalar field. So as it turns out, the retarded Green's function of the dual operator to a charged scalar shows a somewhat similar behavior to what you can see for the fermionic correlation function. In fact, I'm going to give you as an exercise to compute the retarded Green's function for the charged scalar field. Okay, so here is the equation of motion for the charged scalar field. So this is very similar to the uncharged case. The only difference is that instead of the omega squared term, you now have this u squared, where u is defined by this function. So when you set mu or q, the charge, to 0 for the scalar field, then this term vanishes and you get back the equation of motion that we had before. And this mu times q, that is sort of an effective chemical potential for the charged scalar. So if you change q, you will get a different result for the Green's function. Okay, so this is what you will want to solve. You also have to note that as r goes to infinity, so you're approaching the ADS boundary of the geometry, then this term will vanish, so you will have just omega plus mu times q. So omega is shifted by mu q, the effective chemical potential, which means that omega measures the difference of the boundary theory frequency from the effective chemical potential. That is just mu q. Okay, so the exercise is that solve this equation and compute the retarded Green's function for the charged scalar. So you can set, for instance, d equal 3, so you are in asymptotically ADS4 space-time. So you want to set ingoing boundary condition at the charged horizon for this scalar field. And then with ND-solve in Mathematica, you can solve the equation all the way up to r goes to infinity, where you can do a fit on the power law behaviors, read off the coefficients, take the ratio, and that way you can compute the Green's function in dual CFT. Okay, it's good to write a code that automatically does this in Mathematica. So the input could be just the frequency, the k wave vector, perhaps the mass, and the charge of the scalar field. And the goal is to find poles at some non-zero value for the momentum vector, but at small frequencies, small energies. Okay, so this, in the case of a fermion, this would be Fermi surface, where when you're probing the spectrum near the Fermi surface. However, we are considering a boson here, a scalar field. So the question is, what do these results mean? If you find such a pole, what does it mean? Okay, so that's part of the exercise to think about it. Okay, so in the exercise, you studied the charged scalar field in ADS, Reissner-Nordstrom. If you now do a similar calculation, but instead of a scalar, you take a Dirac field in ADS4 Reissner-Nordstrom, then the result for the retarded Green's function will be something like this. Okay, so what do we see here? In the first diagram, I plotted the Green's function and I set the momentum to be equal to 0.9 in some units, where I set the charge, the Q constant, equal to square root of 3 in 4 dimensions. So we are in ADS4 Reissner-Nordstrom. The temperature is 0, So it's an extremal planar black hole. And I set the horizon to be at r equal 1. And the Dirac field has a charge which is equal to 1. Okay, so with these units, k equal 0.9 is the wave vector. And you plot the Green's function. So blue is the real part, and orange is the imaginary part of the a component of the Green's function. And what you're plotting, on the horizontal line you have the frequency, and the vertical line is the boundary Green's function. Okay, so what you see is a giant peak. Here the scale is up to 300, and it's very close to omega equals 0. So it's at minus less than minus 0.001. Okay, so you see a giant peak at this particular value for the wave number. Okay, so you increase k, what you see is that this giant peak approaches omega equals 0, and then goes to the other side, but there is no symmetry. So at k equal 0.925, it looks like a bump here on the right-hand side. Again, we are very close to omega equals 0, with where the maximum lies. Okay, and somewhere in between, in this case, at about k equal 0.918, there is the Fermi surface, where this peak crosses omega equals 0. So you're at a non-zero momentum value and a 0 frequency. So you see this quasi-particle-like peak for k less than kf, and this sort of a smoother bump for k larger than kf. You can also investigate how this peak approaches omega equals 0, and it turns out to be this interesting dispersion relation. And for this particular case, for the parameters omega, the location of the peak goes like k perpendicular to some power z. So remember, k perpendicular was the distance from kf, so this is just k minus kf. Okay, and this z is about 2.09. In particular, it's not equal to 1. So what we found here is a non-Fermi liquid. You can also change the charge of the Dirac field in the bulk, and therefore you change the effective chemical potential. Okay, so these three different plots are results of numerical calculations, and the difference between the plots is the difference of the value of the charge. So this is some smaller q, intermediate q, and some larger q value. Okay, so this omega axis is the same for all three plots, but you see a Fermi surface. So for instance, here at k equal 0.52 roughly, here at a larger momentum, and here it's even larger. So the location of the Fermi surface changes, and you see that the dispersion relation also changes. So what we are plotting here is the spectral function. That's the imaginary part of the Green's function. Okay, so for large values, you see some linear dispersion, although there is still some asymmetry. And as you decrease the chemical potential, the dispersion relation changes. You can also measure the Green's function explicitly and discover a scaling relationship. So if you rescale the distance from the Fermi surface, k perpendicular, that is k minus kf, by some constant lambda, and you rescale the frequency by lambda to some power, then the Green's function basically remains the same. So there's a kind of a scaling law here, and we would like to understand where it comes from. In particular, we would like to understand and determine the value of this dispersion exponent z here. So we found a nice scaling law in the Green's function near the Fermi surface. So we would like to understand where it comes from. So let's go back to the geometry, which was the planar ADS Reissner-Nordstrom charged black brane geometry. So here's the metric again, and the f of r in blackening factor and the gauge field are given here. And the temperature was expressed via this formula here. Let us now set this Q parameter such that this expression here in the brackets vanishes, so the temperature is 0. Okay, now this is the rough picture for the geometry. Here's the boundary of ADS. So this is the vertical direction is r. At r equal infinity, you have the conformal boundary, and at r equal r naught, you have the horizon. Okay, so for large r, the geometry asymptotes to pure ADS d plus 1. Then here in the middle, there is this kind of a domain wall that connects the UV ADS d plus 1 geometry to an IR ADS 2 cross RD minus 1 geometry. So if you've done the exercise, then you know how to get this geometry by taking a scaling limit. Okay, so it seems that there is a kind of an emergent IR CFT. So you see that there is an ADS2 here, so this in principle could correspond to some kind of 0 plus 1 dimensional boundary dual if you forget about this r to the d minus 1 factor here. If you've done the exercise, then you get this metric. So this is just the ADS2 metric, where tau is time direction and zeta is some rescaled radial direction. With zeta equals 0 is the boundary of the ADS2 region, which is roughly here. And there is also a gauge field turned on, which is the remnant of this AT. So A of tau is some constant divided by this zeta radial direction. So there's an exercise. Compute the retarded Green's function by considering a charged scalar field in this ADS2 geometry. So the scalar field is charged, and therefore it will also couple to the gauge field. Okay, so in the Green's function, we found a nice scaling law. And we would like to understand where this scaling behavior around the Fermi surface comes from. So remember that this meant a small k perpendicular and a small frequency limit. Okay, so the differential equation, the equation of motion is quite complicated, so this is not going to be entirely straightforward. And the reason is that the frequency-dependent term in the equation of motion is singular near the horizon. So around here in the ADS2 region. This means that it doesn't matter how small frequency you choose, the corresponding term in the equation of motion will dominate the other terms. So you cannot consider it as a small perturbation for r minus r naught small enough. So here's the strategy that we are going to follow. We separate the space-time into a UV region. So it's basically these blue and gray regions here. And the IR region, which is the ADS2 times RD minus 1 factor. And we're going to perform the small frequency expansion separately in the two regions, so in the UV region and in the IR region separately. And here in this overlapping region, we are going to match the two solutions. So this is how we are going to build the Green's function. Okay, so this is an example for the method of matched asymptotic expansions. I'm not going to explain this in detail. Instead, I'm going to now show you an example for how this method works. The method of matched asymptotic expansions is a very useful technique to finding an accurate approximation to a differential equation which is singularly perturbed. The domain of the function, which is going to be y of x for us now in this example, may be divided into two or more regions or layers where you treat the problem differently. Okay, so let's look at this example. Here's a differential equation, second order equation, and we would like to solve it and obtain this y of x function, and we assume that this epsilon is a small positive parameter. Okay, and let's assume also that we'd like to satisfy these two boundary conditions. So x runs from 0 to 1, and at one end we want this y function to vanish, and at the other end point we want y of x equal 1 to be equal to 1. Okay, so we can separate the domain into two regions. Firstly, in the outer region, where x is order 1, we can try to solve this equation by setting epsilon to 0. Okay, so this will be in the ADS Reissner-Nordstrom geometry. This is the UV region away from the horizon. If you set epsilon equal to 1, then this term drops out and you end up with y prime plus y equals 0, which you can solve, and the solution is some constant a times e to the minus x. Okay, so let's investigate these boundary conditions. Can we satisfy both of them? Well, if y of 0 is equal to 0, that means that this a constant has to vanish, and if y of 1 is equal to 1, then a has to be equal to e. So we see that these two boundary conditions are incompatible. The outer solution in itself cannot satisfy both boundary conditions. So there has to be a boundary layer somewhere where the epsilon perturbation of this differential equation cannot be neglected. So it turns out that it is in the region where x is of order epsilon. Okay, so therefore, we'd like to satisfy this particular boundary condition, y of 1 equal to 1, that's in the outer region. This boundary condition will be satisfied in the inner region. Okay, so we only satisfy this one. So therefore, the outer solution will be just e to the 1 minus x. Let's now look at the inner region. Here in the inner or IR region, x and epsilon are both small. So we can define another x tilde variable, x tilde independent variable, which is just x over epsilon, and this will be of order 1. If we express the differential equation in terms of this x tilde, we get this expression here. And by taking, again, an epsilon goes to 0 limit, we see that this last term drops out, so we end up with y double prime plus y prime equals 0. So y double prime plus y prime equals 0, that has a solution, which is just some constant b minus another constant c times e to the minus x tilde. And here in the inner region, we like to satisfy the boundary condition y at 0 equals to 0. So that means that the two constants are equal, and then we can write down the inner solution. And from x tilde, we go back to the x independent variable, and you see that it still depends on a single constant b. We can determine this constant b if we match the inner and outer solutions. So we can do that in the overlap region, where x is much larger than epsilon, but is still much smaller than 1. So this is the way the two solutions have to match. The x tilde goes to infinity limit of the inner solution has to match the x goes to 0 limit of the outer solution. If you plug in the two solutions, that fixes b, so b will just be equal to e. From the inner and outer solution and the value of y of x in the overlap region, which was just e, you can build the composite solution. So just the sum of the two solutions minus the value in the overlap region, and you get this function here. Okay, so you can plot this function y of x as a function of x, and you see that it satisfies the boundary conditions. Here the value is 1, and here it's 0. And the different curves correspond to different epsilon parameters. Now it turns out that the original differential equation can also be solved exactly in terms of similar exponentials, but you don't get this function. You get a slightly different function. But for these values of epsilon less than 0.1, the exact solution and this approximate composite solution is practically cannot be differentiated in this picture. So it is indeed a very good approximation. After this little example, let's go back to the problem of holographic Fermi surfaces. We have discovered a nice scaling behavior in the fermionic Green's function, and we would like to know the origin of this behavior. So we can try to do a matching similar to the example we had just now. So here is the structure of the bulk spacetime at 0 temperature. Here is the UV boundary, and here's the event horizon. And the inner region will be this ADS2 region for us, and the outer region will be the rest of space-time. Now we want to solve the equation of motion separately in the two regions, and then match the solutions in the overlapping region, which is this here, this boundary of ADS2. An ingoing solution at the horizon, it's represented by this arrow pointing downwards, evolves into a superposition of normalizable and non-normalizable modes by the time it reaches the ADS2 boundary. The ratio of these two amplitudes are just the fermionic ADS2 Green's function, which is written here. So if you solve the exercise for the charged scalar field, you will find that it is very similar to it, except this prefactor is slightly different. So k is the momentum vector, so that's in the Fourier space of Rd minus 1, and it only contributes to the effective mass of this spinor field in ADS2. So this gk is basically just a function of the frequency. And the frequency dependence is omega to this irrational number power to nu, where nu is the square root, and it depends on the mass, the transverse momentum, and the charge of the particle. Here L2 is the radius of ADS2, which is related to the radius of ADS d plus 1. Okay, without going into much detail, the matching gives the following final result for the Green's function. So there's this big ratio here. Let's try to understand the structure and where the terms come from. Okay, let's first concentrate on these black terms here, the first few terms. Okay, so let's set an ingoing boundary condition at the horizon and set omega equals 0 in the equation of motion. Then the wave function evolves, and here in the UV, you can read off the coefficients of the two parallel solutions, and these are going to be in fact b plus 0 and a plus 0. So that is the ratio, as we discussed, is the retarded Green's function. Now, if you do a Taylor expansion in the equation of motion, you can also compute these terms, which are suppressed by powers of omega. Okay, but this is not the full story, as we have also seen previously through the simple example. Near the horizon, omega can never be neglected if it's non-zero. In fact, the initially ingoing solution at the horizon evolves into a superposition near the boundary of ADS2, and this must be matched to the solution in the outer region. And so this ratio, as we've seen, this is in fact the ADS2 Green's function, which appears here and here, and this is the origin of these blue terms here in the ratio. Note that all these constants are real, and that's because the equation of motion is real if you set a real omega and k parameter in the equation. So the only complex quantity is this gk of omega, the ADS2 Green's function. So as a consequence, this will give the imaginary part in the Green's function. If nu is less than a half, then we can neglect most terms in this expansion, and we end up with this simple form for the Green's function, some number divided by k perp, the distance from the Fermi surface, minus some complex number times omega to 2 nu, which is just an irrational number. Okay, so this is the Green's function of a non-Fermi liquid, and you can compare it with the Green's function of a Fermi liquid, where the self-energy had a quadratic behavior in omega, which was subleading compared to the energy. Okay, so this is where the lecture ends. I hope you enjoyed it. Try to solve all the exercise problems, and you can also look at the literature, and we can discuss the problem set next week in the exercise class. I hope to see you there. Bye.